Thank you very much. Feel free to interrupt me and ask questions. Will someone be monitoring the chat? I may not notice. If a chat appears and I don't notice it, just please interrupt. Okay, so one never knows with these courses exactly where to start. I'm assuming that there are some students in the audience, and so I may not be familiar with the theory of symplectic quotient. So I'm going too fast or too slow, just let me know. So M will be a smooth manifold. And G will be a compact Lie group. Acting on M, and G will be its Lie algebra. So then we have a map from G to vector fields on M, which takes a Lie algebra element, and then to any point on the manifold, we want to assign a tangent vector. So that tangent vector is given by you take the one parameter subgroup generated by the Lie algebra element, and you just let it act at that point. And typically, people put a minus sign in to achieve that this map is a holomorphism of Lie algebras. So then we'll take a symplectic form on M is a closed non-degenerate 2 form. And because I'm from the American School of Symplectic Geometry, that will be called omega. And a moment map. So we're going to assume that this is invariant under the action of the. And so then a moment map for the action is a equivariant map from M to the dual of the Lie algebra, satisfying that whenever you take one of these vector fields, so the CM is this this vector field here, then and you contract it with the moment map, then it's D of the pairing of phi with C. And so yeah, so sometimes people put a minus sign here too. There are different conventions for the sign. So what's a consequence of this definition? Consequence is that consider the map which goes from C infinity of M to vector fields. So this is the map which takes a function and takes the vector field, so that IXF omega is df. And then there's this natural map from the Lie algebra to vector fields, and then this means that there's an extension of this diagram, so that the vertical map on the right splits to the space of smooth functions. So that's one of the ways of thinking. A moment map is that for any infinitesimal symmetry, there's a corresponding function. So what are some examples? Any questions before I go any further? So historically, these kinds of functions arose in the study of celestial dynamics. So a typical example would be m equals R4. And I put coordinates here, Q1, Q2, P1, and P2. And I take my standard symplectic form, PQK wedge PK, K equals 1 to 2 in this case. And then it might be that I think of these as position coordinates, momentum coordinates. And it might be that my system has a rotational symmetry. So it might act by rotation on both Q and P. And so then my Lie algebra is just spanned by this single generator. And it's just a one-dimensional Lie group. And the vector field for the action here, I could normalize so that it's something like Q1 d by Q2 minus Q2 d by Q1. That's the rotational vector field for the action on the Qs. And then I do the same thing for the Ps. And then when I plug in the vector field into omega, I find out that this is the phi c for some function phi c, which is Q1 P2 minus P2 Q1. That is, the two-dimensional cross product of Q times P. So this is called the angular momentum in physics, and so this notion of a moment map is supposed to be some sort of generalization of that idea. So a typical application in physics would be you would think of maybe the sun is having much larger mass than the Earth, and then this vector Q would be describing the position of the Earth, and then the Hamiltonian for this system has this rotational symmetry, and you'd like to solve for the Hamiltonian flow. But an example which is more mathematical is you take m equals R4 again, and omega as before. But now you let G, the SO2, act by rotation in Q1 and P1, and then in Q2 and P2. So then the vector field is the sum of the pk d by dqk minus qk d by dpk. from k equals 1 to 2. And then the moment map becomes one half the sum of qk squared plus pk squared divided by 2. Oh, I already had the 2 there in the front. That 2 factor. Or written differently, p squared over 2 plus q squared over 2. So this is, in physics, this would be called the product of harmonic oscillators. So what's the theorem? Which is due to Meyer and Marsden-Weinstein. Is that suppose that G acts freely. On the 0 level set. Then you define the symplectic quotient to reduce space by taking the inverse image of 0 and modding out by G. And this is a smooth manifold, first of all, with a unique symplectic form omega red, so that if you look at this diagram, phi inverse of 0 includes into M. And then there's this projection P to M red. And the condition that the symplectic form should satisfy is that pi star omega is P star omega red. And there are two addenda to this theorem. Let me see, is there some way I can see the audience a little bit better? Nuno, do you want to comment a little bit? Is this about the right speed, or should I speed up or slow down? Or?
Yeah.
Okay.
Rick also says it's the right speed on the chat.
Right speed. Okay. Okay. So there are two addenda to this. This theorem, and one is, you know, what happens when you take Hamiltonian flows upstairs. So suppose I have a Hamiltonian upstairs, which is the superscript means G invariant. So then I can look at the Hamiltonian vector field, and this will also be G invariant. And well, I can restrict this to the 0 level set, This descends to, because it's invariant, it descends to a function h red on m red. And so I can look at its Hamiltonian vector field. On the reduced space, and this will pull back to the restriction of xh on inverse of 0 under this map dp. So another way to say that is that invariant Hamiltonian flows are going to descend to the quotient. And there's a second addendum, which is that a similar thing happens for almost complex structures. So you can say let J be a almost complex structure. Which is compatible with omega. So what does that mean? That means that omega, if I stick a G in, is a Ramanujan metric. On M. And suppose that J is G invariant. So then what you can check is that if I take the tangent space to M, I restrict it to the 0 level set, then this has a splitting into well, first of all, there's a part that is just the tangent space to the level set itself. But then you can check that the perpendicular to this tangent space to the level set perpendicular is exactly this J times G. And I should do something here to indicate that what do I mean by these factors of G? I mean that G underline is the trivial bundle. With fiber G, which is given by the span of these vector fields generated by the action. Okay, well now you can rewrite this. You can sort of think of these factors together as forming a G sub C, complexified the algebra. And then the fact that this is an orthogonal splitting and the fact that J preserves G sub C means that J also preserves the P star TM red part, and so descends to a reduced almost complex structure on reduced space MRED. And this is going to be integrable if J is by the Newlander-Nuremberg theorem. So if we had an invariant compatible complex structure on M, then we also get a complex structure on the symplectic quotient. So something in the chat. Let me just see what it is. Okay. So let's see what happens in our examples. So in the first example, the M was R4. And the G rotational SO2 is acting by rotations in Q and P. And here, if we do the Earth and Sun system, then the Hamiltonian is originally something like P squared over 2 minus 1 over the radial coordinate, which is the norm of the vector Q. So what's MRED in this case? Okay, well, before I said I could take a moment map, which was just Q times P, but I can also equally well just subtract off a constant L. This is also a moment map. All these moment maps are in general. Phi is only unique up to adding one of these constants in space of invariance. So here the Lie algebra is just abelian, so I can add on any constant. So I subtract off L. And so then MRED is, well, I take Q1 and Q2 and P1, but then P2 I can solve for using the fact that the moment map is 0. So this is Q1 P2 minus P2 Q1 minus L. So that means that P2 is L minus Q1 P2. Say that right? No, I've got, I did the same term twice. Hold on. The second term here. The second term here is Q2 P1. So let's see. This is now L plus Q2 P1 divided by Q1. And then I'm supposed to mod out by SO2. Okay, well, let's assume that we're not talking about the case that the Earth and the Sun coincide, so I exclude this possibility. And then I can always rotate so that the second coordinate is 0, and the first coordinate is positive. And then this expression simplifies. If Q2 is 0, this is just L divided by Q1. So what does the H, what happens to the H then? Well, I now just have these two variables, the Q1 and the P1. And I just have P1 squared divided by 2. And then I have minus 1 over Q1. But then I have this term here. The P2 squared is the gives me an L divided by Q1 squared. So these terms here, this is what's usually called the effective potential, and it's just like adding on an additional term which appears when you reduce by symmetry. So if I now do the graph of this potential, Q1 will appear on one axis and the effective potential will be on the other. And then I have some picture which looks like this. And so now there, you see the classification of orbits into the different kinds. If I have sort of an initial starting point down here, then I'll get an elliptic orbit. But if I start up here, say start somewhere up here, then I could get a hyperbolic orbit in this case. Then you have the phenomenon of escape if you have sufficiently large energy. Okay, so that's the sort of physical motivation for this introduction of the idea of moment map is you can reduce the dynamics by symmetry and you get a system which is easier to solve. Or it could be the opposite. It could be that in lower dimensions it's harder to solve, but then by going to higher dimensions, it could be easier to solve in the other direction as well. It depends on the situation. So what was the other example? So M is R4 and H is the sum of the QK squared plus PK squared divided by 2. So here I can think of this as C2, and then their complex coordinates QK plus I times PK. And then this sum becomes just V1 squared divided by 2 plus V2 squared divided by 2. This was the moment now. Sorry, not the H. So then the M reduced would mean I take let's subtract 1 from this so that my my zero level set is not just a point, and so then I get Z1 squared plus Z2 squared over 2 equals 1, and I'm about by SO2. SO2 is the same thing as the group U1 acting by scalar multiplication. So then this gives me the complex projective line. And So this the second addendum to the Meyer-Marsden-Weinstein theorem says that CP1 has a complex structure, which of course we already knew. And so then it's easy to check using invariance properties of this complex structure that, in fact, this is the complex structure on the projective line that you know. So in the chat, it was.
Chris, can you hear us?
Yeah, yes, there was a question about the R4 minus the origin.
Right.
So here it wouldn't matter too much because the zero level set requires that the vector z1, z2 is not zero. But yeah, either way, you'll still get the same symplectic quotient. Any other questions?
No.
So so we wanted to sort of investigate what can we say about the topology of this of the symplectic quotient. So we just gave an example where we started with a vector space, and we got the complex projective line, and so topology can appear under the symplectic quotient operation. And so another example would be if I take CPN minus 1 is the symplectic quotient of CN. And well, I can think of this as having an action. The action of U1 to the n on Cn descends. An action of U1 to the n on CPN minus 1. This was the first addendum to the Meyer-Marsden-Weinstein theorem that closed descent. And the moment map phi. So now it's a moment map on the reduced space to so in this case G dual is just R to the n. So now I have a point in complex projective n minus 1 space, and I've normalized things so that the sum of the zk squared divided by 2 is 1. And so now the h reds are the z1 squared over 2 up to the zn squared over 2. Because that's what the moment map for the action upstairs was. So the image of M red under the reduced moment map is so it's the set of tuples lambda 1 up to lambda n with non-negative real coefficients, so that the sum of the lambda k's is equal to 1. This is just because each of the lambda k's is a zk squared over 2. And I've normalized so that sum of these is equal to 1. So this is now the standard simplex. And so I can think of CP n minus 1 as mapping to this standard simplex. By the moment map. And each one of these faces corresponds to some locus where one of these coordinates is equal to 0. And we know, what the homology of CPN minus 1 is. So this is Z in degree 0 up to 2n minus 2 and 0 otherwise. And it's generated by the complex projective spaces of lower dimension. So in the case of CP2, you have 3 generators. You have the point CP0.
You're looking at cohomology, right? I guess. Is it the
So you have the duality. So
yes,
I can either think of
yeah.
homology or cohomology. So when I write CPJ here, I could either mean the homology class or I could mean the dual cohomology class. So so let's see. So I have CP2 itself. So that would be a top degree homology class or a bottom degree cohomology class. I have the CP1 here, and then I have the CP0. So I have 3 generators. Here, each of think of cohomology or homology. So so this generalizes to some more generally. Suppose I have the same action. The moment map is given by this zj squared divided by 2 minus some constant cj. And so let G be a subgroup. Of U1 to the n. So it's generated by some vectors C1 up to CK and in Rn, which I think of as the Lie algebra of U1 to the n. So then the moment map for G has has components. Let's call these components phi G. So then I pair these guys with CIs for I equals 1 to K. And then I can take the symplectic quotient by the action of G. So if I would take the action of U1 to the n and take the symplectic quotient, I would just get a point, because then I would be fixing the norms of all of the Z squared and then modding up by the phases. I wouldn't get anything interesting. But if I mod up by a subgroup, then I get something that's interesting. So then I get what's called a symplectic toric manifold. But it also, by the addendum to the Meyer-Marsden-Weinstein theorem, it also has a complex structure. So these turn out to be the same as what are called projective toric varieties. And the action of U1 to the n descends to an action of U1 to the n. Well, you don't necessarily need to mod out by G. You can just say, you know, U1 to the n acts on this MRED, and the image of this toric variety under the action is just all of the n tuples, so that the pairing of each of these n tuples with, let's see, did I call it I or J in the previous page? Called it I. So I want the pairing of lambda with each of these CIs is equal to CI for I equals 1 up to K. And I'm taking the non-negative real numbers in each entry. So the idea is you start off with this sort of generalized ortho, and then you're slicing it off some by setting, imposing some linear qualities between the different coordinates. So this would be the case when the MRED is BP2. And so the polytope would be the 2 simplex. But you could slice in other ways. So you could, for example, get a square when you do the slice. And so then if the polytope is a square, then this would be the case that MRED is CP1 times CP1. And so on. So what can we say about the cohomology of MRED in the toric case? Well, there are 2 parts. There's the additive generation. And there's the multiplicative generation. So maybe I should make sure I'm not going too fast and just say any suggestions for generating an additive basis of the cohomology or homology here. How would you do it if you needed to find a basis for the homology, for example? Okay, well, the lemma is that the homology in this case is generated by the inverse images of the faces of the polytope. So in the case of CP2, you know, the inverse image of a vertex would be a point, the inverse image of a face would be a CP1, and then the inverse image of the whole polytope would be CP2. So you get a basis by that. Here I'm taking all faces, so there are going to be some linear dependencies between the faces. And one way of doing this is using Morse theory. There are many ways of seeing that this will give you a generating set. So if I take a generic vector, and then I pair phi red with nu, so then this is a function on the reduced space. Then this will be Morse. With critical points, the inverse image of the vertices of the polytope. And then you check that the stable and unstable manifolds are inverse images of faces. So then right away, the fact that the unstable and unstable manifolds generate the homology from Morse theory tells you that you get a generating set. Okay, but then you can do a little bit better, and you can get a multiplicative set of generators. And here, multiplicatively, they're just generated by the inverse images of facets. So remember, a facet means a codimension one face. And so how do you see this? Well, this is just because any face is an intersection of facets. So if I call my face F and my facets are F1 through Fk, then in particular, this means phi inverse of F is the intersection of phi inverse of F1 through F inverse of Fk. But when you go to the dual cohomology classes, so each of these smooth manifolds has a dual cohomology class. That just says that the dual classes well, now I have the cup product. Give me any inverse image of any phase. Multiplicatively. Okay, so I think I'm out of time. I was going to end by saying what the relation.
Yeah, we can give you a few minutes, up to 5, if you want to interrupt in some natural place.
Oh yeah. Well, let me just write one more line there. I don't want to keep people.
Fine, sure.
Yeah, but the point is now that it's pretty easy to see what relations are. So there's some relations, the relations of two kinds. They're relations on the classes which are the inverse images of the facets. So you already saw in CP2 case there are 3 facets, right? But we know that H2 of CP2 is dimension 1. But all of these 3 facets, they represent the same homology class of a line in CP2. In fact, all of these lines are deformable to each other. So, they have to represent the same homology class. But the other type of relation is when if facets have empty intersection. So in this case, in the CP2 case, if I take 2 facets, they intersect, but if I take 3 facets, there's no intersection. So then obviously, if the facets don't intersect, then the cup product is the cup product of the intersection, and that's just 0. So these are all the it turns out these are all the relations. And maybe I'll start next time with just giving a citation for this result. But so yeah, this is a complete description of the cohomology toric varieties, and we want to use vortices and equivariant cohomology to sort of understand this result and generalize it to quantum cohomology. Yeah, I'll stop there.
Okay, so let's thank Chris now. So any questions here? So there is one question.
So what can you repeat what the relation A is?
Well, the relation A is there'll be some relation on the degree 2 cohomology classes, and what I mean by this is that it might be that the two facets represent the same cohomology class.
Okay, but you're not giving a method of identifying that in general, right? Is this just an example?
Well, there is a general formula for how the divisor classes relate. So there's the point is that there's a the facets correspond to the basis vectors of Rn.
Right.
And there's a map from, you think of Rn as the dual of the big Lie algebra, and then there's a map of that to the dual of the Lie algebra G that's acting, and that will have some kernel, and that will give you the relations among the
Okay.
classes. Like, for example, facet 1 and facet 2 are equivalent. That's because the vector 1 minus 1, 0 projects to 0 when you go from the Lie algebra of the 3 torus to the Lie algebra of the circle. So So it can be read off from this. Where did I have? Yeah, so G was a subgroup of U1 to the N. And there's going to be, or there can be one facet for each basis vector of the U1 to the N, and then there's some projection to a smaller space, and the kernel of that map it determines what the relations in each two are. But it's just combinatorial. It's not.
Okay, okay.
No.
Ritwik has a question on the chat.
In example A, right. Yeah, that's exactly right. So the fact that we're thinking of the multiplicative generators as the facets. In particular, if you did this computation for CP2, so in CP2, I could represent L by this line, but I could also equally well represent L by this line. It's the same homology plot. And then L squared, so let me think of this as L1 and this is L2. L squared would be then L1 up product L2, which is the same as L1 intersect L2, which is the plot of a point. Yeah, so that would be equivalent to saying that L self-intersection number 1, which I think is what was that your question? Yeah, exactly. So then if you take another line, L3, but L3 is still equal to L, and then you see that these three facets, the common intersection is empty, and then that's saying that L cubed is 0. So that then the description of the multiplicative description of the homology of CP2 is to say that it's generated by this line class with a single relation. L cubed equals 0. That's right. Any other questions?
Don't have any more questions. So I think we can thank Chris again.
Yeah, enjoy your dinner.